Hello. In this video we're going to continue with our CAD simulations using LTspice, and we're going to look at distortion analysis, and then we'll move on to temperature sensitivity. So for distortion analysis, I wanted to point out in your lab manual it states that total harmonic distortion is defined as the ratio of the equivalent root mean squared voltage of all the harmonic frequencies from the second harmonic on over the RMS voltage of the fundamental frequency. The fundamental frequency is the main frequency of the signal. So in our case, we're using 1 kilohertz for this lab. And to be able to see what that looks like, this is what the equation looks like. This is your root mean squared. This is summation notation. It starts at the second harmonic. And so second harmonic, third harmonic, fourth harmonic, however many we see, we're going to square that and then take the square root of it. And that's all divided by the fundamental frequency, which for our case would be the magnitude of whatever 1 kilohertz is. So I know that probably sounded really complicated, but it's fairly easy. And if you've never taken a fast Fourier transform, that's okay. We're going to do it step by step right here. So to take a fast Fourier transform in LTspice, we would just put in your transient analysis, and I'm going from stopping at 104 milliseconds and starting at 100 milliseconds to give myself time for the circuit to stabilize, and then you just run it. And sorry, I have a pet peeve. I can't look at the graphs when they're on the bottom. I like them to be on top. Okay, so we look at the output, and then we right click on the signal on the waveform, and then you go to View, FFT. Our output node is node 12, and we just make sure node 12 is highlighted and press OK. And so this is the FFT. And looking at this, you might think, well, the whole thing's noisy. Well, what we're going to do is we're going to change the y-axis from decibels to voltage to make it linear. And there we have it. So this big spike is our fundamental frequency. And then you can see this little bit of distortion on the second harmonic. And so let's measure that. So you want to get the cursor close and then just use your key on the keypad to make it like right at 1K. And so at 1K we're getting 806.5 millivolts. And then on the second harmonic we're getting 10.33 millivolts. And then looking at this graph, it doesn't look like there's anything else out here. So going back to our equation, since all we have is the second harmonic was 10.33 millivolts, you'd take 10.33 millivolts and divide it by 806.5 millivolts, which would end up being 0.0128, and you would multiply that by 100, and you would get 1.28% total harmonic distortion. And so going back to the linear chart, again, it didn't look like there was any distortion out here, but I wanted to point out here around 2.5, notice how small this is. It's in the microvolts. And then when you get closer to 3, Now we're seeing a little bit of distortion, 1.188 millivolts. But looking at it, you can't really see it there. So I just want to show you how to do it using decibels. And looking at this, what I would do is I would just take these 5 peaks and I would ignore the rest of this stuff. And so we took the first one, and now that we're looking at decibels, right? So negative 1.867 decibels. So when you're looking at decibels, we have to convert it, which the conversion's, really simple. So you would just plug in the decibel value here, which would be, what was it, negative 1.867, and it would give you the voltage output. And so you would do that for each one of these peaks. This one's the negative 39.7, negative 58.49, and you just document it and then convert it. And so I just created a chart in Excel, and this is the negative 1.867, and then to convert it you would do and that is exactly what we had on the linear scale for the fundamental frequency, right? 806.5 millivolts. And then you could just take this, and then that, right, the second one was 10.33 millivolts. Okay, and so what you do, let me show you another. So now that we have all the voltage amplitudes, the first harmonic is 806.5 millivolts. And so what we would do is that fundamental frequency is on the bottom. The second through fifth harmonic, you sum them together and take the root mean squared. So you sum them together, you square that, and then you take the square root, and then you divide it by the fundamental frequency. So going back to the Excel sheet, that's what I had done here. And you would multiply it by 100 to give you the percentage. So it would be 1.44%, which is a little different than what we got on the linear chart. The linear chart we got 1.28%, and on the decibel chart we got 1.44%. So I would use either method, whichever seems more comfortable to you, and just take a screenshot of your graph and document your results in your lab report. Okay, so moving on to the temperature sensitivity. So in the temperature sensitivity, you still want to have a transient analysis. So you'll keep this directive. And then we're going to go to the .op, or you could press S, and we're going to type .temp negative 40, and so that means the first sample is negative 40 degrees Celsius, and then 25 degrees Celsius, and then 100 degrees Celsius. And then I'm going to go ahead and place this down here. And I got these values from the lab manual. So common temperatures to rest are negative 40, 25, and 100 degrees. And 25 Celsius is about room temperature. So you put that directive in, you run it, and then you have these multiple plots. And so maybe you're looking at this graph and you're not sure exactly which one is the first one. Which one's negative 40? Is it the green one or the blue one? Well, if you look at the color of your node title up here, that is the color of your first sample. So negative 40 is this blue one, and you can tell that the voltage is lower than the rest of them. So then 25 is the red one, and the green one is 100. And we notice that at 100 degrees, we're getting more voltage on the output. And so, what could cause more voltage on the output? It would be more current going through the collector. And so, what devices are affected by temperature? It'll definitely be your transistors. And so, it's kind of interesting to see what happens when you change these values. So instead of going to 100, let's try pushing up to 150. And, let's see what happens when this thing's at like negative 200 degrees Celsius. So yeah, see how far it dropped at negative 200 degrees Celsius, and then at 150 degrees we start to see some clipping. So that's too hot for that transistor. But it looks like through simulation it could run at 120 and we're not getting any clipping. So again, do the negative 40, 25, and 100, and you would just take a screenshot of this and then talk about, why is the output higher or lower? What's causing it at the end through temperature. So it'll take a little bit of research to come up with your discussion points, but that's all. That's what I have for the distortion analysis and the temperature sensitivity, and I hope this helps. Thank you.